Okay, it should be live, but there is a delay here. Let me see if I can fix that. Ah, we should be live. So welcome everybody to this experiment in which I am doing research live, and I have seen that well, maybe we wait 5 minutes for more people to join. Oh, hi Malcolm. So somebody is joining. Okay. So I guess I can't trust at all the statistics. Okay, no, some people are coming in. Okay. So yes, I've seen that some people are actually watching this stream even afterwards. I see in the statistics that some people stay there for an hour, so I guess they're really watching the whole thing. So if people can introduce themselves so that we get to know each other, and it's a little bit nicer. Otherwise, it's just me talking to myself. So. And if people want to write, as I said, if people want to write in the chat who they are, what they're interested in, and in the meantime, I'll get right to work. And of course, I did the thing that I shouldn't be doing, which is engross. Okay, so I think I'm set up. I'm still learning how to do all this. Okay, so I should review what we did last time because I'm sure there are gonna be a bunch of mistakes. And so let's get right to it. So first we had started with unitary revolution, then we realized we should start with the Schrödinger equation. And why don't I make the text a little bit nicer here? So we start with the Schrödinger equation. We will have to review the text at some point, but the point is that we have the Schrödinger equation here. Okay. Okay, so we now want to write the evolution as an operator that acts on a wave function. The infinitesimal time step is going to be, and then here we begin the equation, and we want to say that psi of t plus dt equal psi of t plus d psi of t, and we put an end here, and then we say that this is psi plus dt. Okay, we should have it from the Schrödinger equation, so this times dt, and so this is going to be equal to psi of t plus, and this is where I had it wrong here, this should be frac h dt over I math h bar, right? Oh, I need an align. Okay, and it's aligned. No? What? Oh man, I always forget this. Yeah, begin align. Begin equation, begin align. What is your problem? Missing a dollar. We shouldn't have any dollar. Well, we need this, so that's for sure. Okay, still complaining. So insert command slash t. Oh, there you go. Oh, hi Nick. Am I waiting for your replies for you guys to set up the meeting next week? And this is okay. So that's the thing, and this we can wait a second. We are missing a psi here, right? How do we want to do it? Yes, we want a psi here, and then we are gonna have this is one, and this is where I still need to understand what to do, whether the identity should be a 1 or it should be an I, but for now let's call it a 1. And so now this thing becomes the operator. There we go. And we need this, and we need the backslash here. And we need the left, and we need the right. Okay, and that's our U of dt. There we go. Of course, I need to let this go. All right, very good. So we found the usual thing. And now note that since H is a Hermitian operator, the UDT is a unitary operator. In fact, and then we can do the little math, which is probably in all the textbooks. We are gonna do this, and then we're gonna put a dagger here, and have you ever tried the typist instead of latex? We're trying to write a paper using it currently, much more convenient. Yeah, I don't love latex, but I already have the experience, so I don't know if converting to something else makes me lose all that experience. So how does typist, does it support the same syntax? And for tickets, is there some package that is equivalent? I have no idea. What I'm also trying to understand is whether we can make this a little bit more interactive with other people. This is something that I was discussing with one of my students, if we could have this a little bit more interactive than just me typing. And I haven't figured out. So if you guys have any idea of how to make this session such that I can still work, but then there are other people that I can actually do something, is just looking at me. Also, the chat, we are realizing that has very low bandwidth. So yeah, I still don't know how to do this, but at least I'm getting something done. So that's a little bit the point. Okay, so I need to prove that this thing is unitary, and that's gonna be this. Oh no, I should just use this. There you go. Which is this. Tac tac, and then we put a dagger here, and then of course we are gonna do the usual things, and then this is going to be another. So now the dagger goes in. Why did this come in? This shouldn't be there. The dagger comes in on the 1 and on the H. Oh, I lost a piece. I lost the left. Let's see. Okay, so this one done. This is gonna be. Oh, the I gets a minus. Okay, that's what I need to have here. So I was starting to worry that the thing wasn't doing the thing that was supposed to do. So let's do it like this. So okay, so this should be clear. Well, the one I will just assume that people understand the real constant don't get a minus sign, and now I have the 1 minus and the 1 plus. And then so H is equal to H dagger, and we get the minus sign, we bring it in and put it here. So now this becomes clearly 1 plus this thing square. Wait a second, I'm missing a dt somewhere. I lost a dt before. I know it's inside there. Okay. Sometimes I get confused by what I do. Okay, so I have this part here. Okay, so I'll finish this and then I'll look at the chat. Okay, so this is square. And then this means that it's 1 plus O of dt squared. And so we are going to say that this is a unitary operator. Okay, let's check. Oop. Okay, so I have this dagger, so we said UDT is this, UDT is here, this is here, the dagger goes in, goes on the H, goes on the I gets a minus, the H remains the same, this is just 1 plus, here, plus minus. There you go. And then it gets, and there you go. Okay, so what's on the chat? So yes, people are starting to talk about typists. This is to make this package, but there compensation updates in real time. So the problem of multiple people editing it, it might be a concern for me, because at the end of the day, I need sort of to understand what the copyright is, and so having too many people, touching, then it's not clear whose contribution is who. And this is, unfortunately, I really hate copyright, but unfortunately these things need to be done, and so I don't understand how I would be able to do it sort of collaboratively. It's why, because there is also overleaf in principle, but I can't just take overleaf and open up to a bunch of people that I don't know who they are and so on. So I really don't know how that works. And Marco, you can try asking for the questions, and then if it's going to be too much time, I'm going to tell you it's too much time. So, you know. Okay, so we proved that. Now we have to go the other way around and show that if we have an infinitesimal operator that is unitary, then it can be written in that form. This works the other way around. If we have an infinitesimal operator that is unitary, we can express it as we can express it in that form, and then with the English we're gonna have to fix it. That is okay, so let's get the math right. So we know that this thing, so we know that the first order, so now we don't know what it is, so we know that it can be expressed as something like this. So we know that there is a UDT, and we can say that it's going to be one let's write it like this. So we know that if we apply that operator to that thing, that's going to be a psi of t plus some derivative d psi of t in dt. Okay, so we know that we have that, and therefore this thing is going to be 1 plus something. And so this thing can be written as 1 plus some operator, let's call it O of dt. On psi of t. So we can do that. Then we're going to say that this dagger u, it's now not going to be this thing, but it's going to be this O dt, and it's going to be O dt. And so now we are not going to be able to take the dagger away because we have no idea what O is. And this is my O dt. Okay, and now we have the expansion with all the different terms. So we have the second order term, which is going to be O dt squared, and then we have the first order terms, which are going to be so O dt is going to be O plus O dagger. Oh yes, hopefully. Okay, so let's check. Okay, so I have an operator that advanced time, and I know that it's infinitesimal, so I can put echo. There you go. I'm already missing a D because I keep putting this backslash before the D, which does not make any sense. Okay, so yes, I have definity, and so now I can write this thing as an O, and so I have plus 1 plus O, and this T should be lowercase. And then, okay, so I know that this thing is expressible like this. So now I do the computation. This becomes there. And so I have 1 times 1, 1 times O dt, O dagger dt times 1. And then that's not exactly how it works. So let's fix that. It's O dagger O dt square, and so this is that plus some higher order. I put the O here. No, it doesn't work. I need a different name for that thing. Let's call it geez, otherwise it's too confusing. There are too many O's. I hate notations. They always come back to bite me. Let's call it, I can't call it U, I can't call it O, I don't want to call it P. Let's just call it A and be done with it. Okay. A, 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 A. Okay. Okay, so I got it here. This becomes 1 plus A. This is from A dagger and 1 plus A. This gets the dagger, so 1 1 dagger A and A dagger A. Now this is O dt squared, so that it's clear what's gonna happen. Okay, so the other question about a typist, does the archive support it, or it's something that I can't put papers in the archive anyway? Because if I can't do that, it's basically already a no-go. Okay, so, and now we say, okay, now since if we want the operator to be unitary, then we must have that A plus A dagger is equal to 0, which means A is self-adjoint. We call them self-adjoint or Hermitian? We should probably call them self-adjoint, even though that's a whole kind of world. Okay, which means it's self-adjoint. No, it's the opposite. It gets a minus sign. That I math A is self-adjoint. Okay. This is going to be self-adjoint, and so why don't I put it like this? What's the other? So self-adjoint, how I call the one that gets a minus sign? Anti-self-adjoint? What's the name? Okay, anti-self-adjoint. What's the name? There must be. Adjoint. Operator self-adjoint. Oh man, I don't know how to call it, which means A is, so we'll just call it anti-self adjoint for now. I'm sure that there is another name that is more proper, and I don't remember off the top of my head what it is, which means that it can be expressed as, which means that IMAF A is self-adjoint, and by rescaling constants we can write it as, okay, so which means that we can write it as A equals frac of H over IMAF H bar, where H is a self-adjoint operator. And this means that the following condition that so the evolution follows the Schrödinger equation. Okay, so now the condition is this. This means that is equivalent to, and then we put the condition of the Schrödinger equation. Okay, so this is probably what I wanted. So since it's continuous, we can understand that the continuous system is, and this is it. Okay, so that's good. Anything that makes a PDF is okay for ArcSys. Okay, so ArcSys is not going to build it, and okay, that's how it's going to work. Okay, so Malcolm asks, the wave function are always in terms of complex exponential, right? I mean, it's a complex function, so you can always write it as rho times e to the I something. So you can always put the exponential, but the exponential is just the form of the complex number. There is nothing specific to the wave function for that. What is it? The polar coordinates for the complex number, the polar expression. There's something, again, I forget all the terms. Okay, so now, okay, so now we had this from last time. The thing here that didn't work, that Tobias pointed out, was that this step is a little bit too fast, saying that this for all must have, this is not what it happens. Here we're saying that conserves the norm, but the real thing is using the polarization identity, which we can probably re-get from Wikipedia. Polarization identity. And it's the fact that you can always express the inner product as essentially norms. So there it is. Okay, so let's start copying it, and we are gonna copy it. Okay, so representation that preserves the norm of all states is a unitary operator. So we are gonna take it here. We are gonna say that. So this I don't need. We have psi. Okay, phi psi equal 1/4 Okay, the norm of phi plus psi square minus the norm of the difference minus I math the norm of phi plus I math phi psi plus I math, and I put a minus I math. Okay, so okay, this is because the inner product can be expressed through the polarization identity in terms of the norm. There we go. And so thanks Tobias for telling me this and keeping me honest. Okay, I'm getting a bunch of errors. Why am I getting errors? Where am I getting errors? Bad delimiter. And why do I get it there? What is the bad delimiter here? Okay. Psi minus... Ah, jeez, I hate these errors. Okay, it's inside here, but this was not... This is not the thing that I just added. Is this the problem? It really feels like working in C++, where you get errors and they have nothing to do with the thing that is actually the problem. Where is the polarization identity? Is this the issue? Yeah, exactly. So it's the problem is inside here. Ah, it's math instead of I math. There you go. There you go. Hi Tobias, I was just mentioning you because I added the polarization identity to go from norm to inner product. And what we did was essentially I went through the beginning and went through a little bit better from the Schrödinger equation to unitary evolution, and now I was fixing the fact that another condition is preserving the norm, and I'm essentially going through the whole thing and make sure that the thing still makes sense after a week that I've looked at it. So, and then the norm, okay, and then, so we got this, the condition evolution preserves the norm is equivalent to the unitary condition, and we now look at okay, this is because there can be a spare. Okay, so I have to say if the norm is conserved, then the inner product is conserved and the evolution is unitary. That's kind of another condition. The fact that the evolution is unitary is just that this expression is right, but the fact that the inner product is conserved is a different condition. Okay, yes, that should also be there. Okay, so note that if the evolution is unitary, then the inner product is conserved. In fact, I don't know, you guys, I like having all these different conditions spelled out in my head, that all these things are in principle different, but are all equivalent. I like these sort of things. So if I have, let's say, a phi and a psi, and I apply a unitary operator there, then this becomes psi and u dagger and u and psi. Actually, that should be a phi. This should be a phi, and this becomes just the inner product between the two things, phi and psi. Okay. Condition, the argument works in reverse as well, therefore this is, the evolution preserves the inner product, and then this means this thing. And then we want a delta t, and we want a delta t here, and we want this to disappear. All right, and we need a dollar here is equivalent to the condition of, why is this underlined? Oh, well, I need a different name here. Condition inner product preserved. And it's not going to be unit, but it's inner. Oh, it's just in. Ok. Quindi in particular, we don't need all these, in particular, unitary evolution will preserve the norm of vectors since psi square equal psi psi. And then we don't need this because we proved it more in general before. Okay. Okay, particularly the integration will preserve a universe, so this is equivalent to inner product preserved. I need to do it like that. And this. Okay, so then this was the fact of the projection now, because I did that as well. So now we look at the square of the inner product between two states and is close. Probably there is a shorter proof in terms of this. Because the square is the square of that preserved. It's well, it wouldn't be. Okay, now probably it's better like this, because then you see that the Hermitian parts simplify, and which means that the projection or initial equivalent, that the change of state is orthogonal to the initial state, and that the conversion is true. Square the inner product. Oh, and then okay, so the equivalently was that. Okay, so this is this is psi t plus dt. So if we time evolve of one timestamp and project to the previous, then the norm is 1, and which means the projection on top of the variation is 0, and so these are perpendicular, and then there is the characterization in terms of orthonormal bases, and so given the unitary evolution preserves the inner product, therefore the unitary evolution maps an orthonormal basis to another orthonormal basis, and so on. And let's see the math. So we have two states expressed at different linear combination of the same orthonormal bases. We take the coefficients out, we evolve the orthonormal bases, because this is just the coordinate delta is going to be equal to this, and then we move the things back in, and then this is just going to be the evolution of that, and that's it. The formation in time maps, orthogonal basis. So I think I just want to have all of this in terms of dt, because that's what we have been doing anyway, and so it's more consistent. D, and let's see if I got them all. Okay, so these are all the conditions, the mathematical conditions that we have. We have essentially the Schrödinger equation, then we have unitary evolution, preservation of inner product, preservation of the norm, preservation of the square, of the Born rule, and the preservation of orthogonal, so it's 5 conditions, and 6, it's 6 conditions, yeah. 6 equivalent conditions to the Schrödinger equation that are just mathematical. And now we had the information theory one, and so when looking at classical mechanics, we saw that Hamiltonian mechanics implied conservation of entropy. The connection is still present in quantum mechanics. Let psi of t be the evolution of a density operator. Let psi of t the diagonalized expression for the density operator, where the bases can be in general different at each moment in time, given the linearity of time evolution. The p is equal to p. This, I'm missing an operator here. The evolution will be u of dt applied to the whole thing is equal to the decomposition in the new basis. That is, the coefficient of the probability distribution over the basis remain the same, only the basis changing. Since the entropy only depends on the condition pi, the entropy remains unchanged. The converse is true. If an evolution preserves entropy, then it is unitary. First of all, note that pure states are the only states with zero entropy. Therefore, pure states must be mapped to pure states. Now consider two orthogonal states. An equal mixture of two will give us a maximally mixed state over two pure states. That means that given linearity, a maximally mixed state over two pure states can only be mapped to another maximally mixed state of two pure states. Therefore, orthogonal states must be mapped to orthogonal states. This means that the evolution that preserves entropy must map an orthonormal basis to another orthonormal basis, and therefore it is a unitary evolution. That is, condition the evolution preserve information entropy is equivalent to that. There you go. And then any way to relate unitarity to von Neumann entropy conservation? Yeah, that's exactly what this is doing. So it's another condition that it's equivalent. The fact that the inner product and the norm are equivalent, guaranteed by the operation, should be physically interpreted. Yeah. So all of this now we're basically going to take all of those things and give physical significance to it. That's sort of part of the game. Like first we fix the math, and we know that the math is what it is, and then we give it some physical interpretation. And I just want to check the notes because we had a bunch of things that we had as a list. So orthogonal states remain orthogonally equals unitary evolution. We have it because we preserved the orthonormal basis. Inner product between state and state and next step either one unitary evolution. We have this. Okay, so all the math thing, I don't have any more math ideas. If other people have math ideas, we should put them, but let's just start with the physical things. The parallelogram law apparently identify exactly the norms that comes from an inner product. Yeah, so the geometry of all of the polarization identity, it's something that still escapes me. I mean, I kind of understand it in the real case. I don't understand it in the complex case. It would be nice, because at the end of the day, to talk about the inner product, you only need a space of dimension 2. And so it would be nice to see geometrically exactly what the inner product is if we think as what's his name, as a two-dimensional complex vector space, as essentially of spaces of complex planes, of four-dimensional complex planes. So there must be a geometrical interpretation. By the way, I see my video here being very choppy, that sometimes slows and goes fast and slows and goes fast. Do you guys see this, or is it just a local thing that I have? Because I've been having problem recording using my laptop, and I had absolutely to stop. So if the streaming is not smooth, I will change computer and try to stream from my desktop instead of my laptop. Okay, so the video is choppy, but the audio is fine. Okay, I think I'm gonna stop using my poor laptop. It's poor laptop. It's a new laptop, and it's worse than the old one. Okay. So I need to set up my desktop. Okay, so we have this. Oh, it's smooth for Nick. So the Nick, the video doesn't like slow down and then suddenly go fast and then go slow down again. No, it's. I'll look at the recording on YouTube and see what happens. Probably that's the most reliable thing. Technology. Okay, so we have conservation of probability. Now I want to do the. Okay, so I have the conservation of probability. What did I mean by that? we can start with this. Oh, it changes. Right now it's smooth, but sometimes not. Okay, it's completely unreliable depending on what the minimal load on the laptop is. Very finicky. Can I increase? Let's see. I'll try increasing the priority of OBS. Can I say that? What? I used to be able to do that, right? No, I can't. This is very. Huh. In Windows 10, I used to be able to make priority higher of processes from the task manager, and now I cannot do that anymore. Unbelievable. Yes, let's remove functionality. Oh, maybe this because I'm not. I didn't start it as an admin. Vabbè. It's gonna be whatever it is for now. Okay, so let's start with. So what did I mean by conservation of probability? I don't quite know what that means. Okay, we can do the continuous sequences of measurement. Okay. Let's put it before here. And say, let's start a section physical. Now I know what I meant. I meant that, yes, okay. So that's gonna be, so what should happen is that I can predict the final state with 100% probability. That's what I meant, meaning that yeah, also the distribution spread is preserved. That's something that that I might want to put as this sort of preservation of uncertainty. And you know, so and again, that basically is it's actually distribution itself is conserved. It just moves to another observable, right? Because you change the observable through like the Heisenberg picture, whatever, and the distribution is actually exactly the same. And so that also is a unitary evolution. But okay, so we first want to drive the point of determinism, that Schrödinger equation is determinant reversibility, meaning that if I know the initial state, then I know exactly the final state. And therefore, if I have probability 1 for a particular state, I will need to have a probability 1 for the final state, and that's the conservation of the norm, and that's yeah, okay. So okay, so okay, let's put it like this. In classical mechanics, we saw that Hamiltonian evolution was equivalent to determinism and reversibility. The same applies to quantum mechanics. If an evolution is deterministic and reversible, then knowing the initial state means knowing I can't find it, and knowing the final state and vice versa. Given that quantum mechanics is a probabilistic theory, this translates as being able to predict the final state or reconstruct the initial state with 100% probability. Mathematically, this means that if we start with a pure state psi of t with normalized 1%, meaning that it is maybe we can do it okay, so this means if you start with a pure state, and let's have it in like this, psi of a pure state, let's call it rho of t equals then the final state will have to be rho of t equal this plus let's put delta at this point here. Okay, and I think I missed this. Okay, so now we have to make the argument, translate the argument into math. I'm putting this, that's what I'm doing. Ok, e magari è plus delta t here as well. Reversibility of t is relative with the final state. The this means that the norm that this means that if the initial, okay, okay, given that both rho of t and rho of t plus delta t are trace one operators, if the norm of let's just got it. psi of t the norm of both psi of t and psi of t plus delta t must be unitary. There is a deterministic and reversible evolution must preserve the norm of the vector, must preserve the norm, which means that okay, deriv condition that rev dr how do we call it in classical mechanics, this thing? I should have the book that agrees along the two chapters. So let's go and look at what these are called over there. Reversing Hamiltonian mechanics. It's called dr EV, deterministic and reversible evolution, and the text is deterministic. The evolution is deterministic and reversible. Okay, and then we can go to the information theoretic one. When looking at classical thermodynamics, we saw that determinism and reversibility at a conceptual level is equivalent to conservation of information entropy. This connection is still valid, and if it wouldn't be valid, it would be a problem. Okay. Okay, so did you define your own macro? Yes, I did define it. I actually got the idea from a Lorenzo Maccone when we wrote a paper together. He had this trick, and I said, "That's a very nice trick," and so I stole it. So yes, it's a lot shorter. So what's the different underlying difference between classical and quantum states? If the Hamiltonian evolution then it works for any quantum states, but classical states may be fail. No, so the Hamiltonian evolution in classical and quantum mechanics is exactly the same. It really works exactly the same. In fact, the structure of phase space in classical mechanics and quantum mechanics is exactly the same. What we are trying to go for, like the sense that we have, is that the real difference between classical and quantum mechanics is that in classical mechanics, you can have states that are where the distribution is spread as small as you want, and in terms of entropy, you can have the states at as small entropy as you want. You can take negative entropy and make your Gaussians as small as you want, and at the limit where they are delta Dirac, they are actually one point in phase space, that would be a minus infinite entropy. What we in quantum mechanics instead, you have a floor at the entropy. The entropy cannot go lower to zero, and that makes sense just at a thermodynamic level. Like you can't have negative entropy. It does not make sense. So it's in our mind, quantum mechanics is really just fixing that. It's just putting a zero to the entropy. In fact, I'm going to prepare a video for next month showing how even if you just take that premise in classical mechanics, you can get a lot of effects that are quantum, but you have them in classical mechanics. So that's really the real difference. The problem is that I don't have a nice tight mathematical argument to show that just because the math is complicated and I don't have the right mathematical framework to do that. That's part of the physical mathematics is that. But for a qubit, classical phase space is larger than quantum. Bloch sphere is inscribed to a probability simplex. No, in the sense that the linear things, how can I describe this? So the qubit, so a qubit in classical mechanics, a bit is just a segment geometrically. You have the 0, the 1, and all the probability in between. So you really have a segment. In quantum mechanics, it becomes a sphere. So you have the 0 and the 1, then you have the sphere. The axis in the middle, it's the classical bit that you can extract. And then you have a sphere, right? And in principle, you can embed a simplex, a four-dimensional simplex, a triangular pyramid inside the Bloch sphere. But the issue is that the relationship of the entropy are not going to be the same, in the sense that only the axes go through a point with 1 bit of entropy. If you take any line, any other segment between two pieces, two points, you never go through the 1 bit. So you can never extract 1 bit. You can only extract 1 bit between two things that are orthogonal. The classical analog of the qubit would actually be, because if you think about a qubit in classical mechanics, it's the state space for a spin 1/2 system, which basically gives you a direction in space. In classical mechanics, you have the same thing for, let's say, the state of a polarized magnet, whatever. Like it's something that where the state is a direction in space. And then you're going to have conjugate variables in the same way that you have a spin 1/2 system, where the conjugate variables is the vertical direction of the polarization and the angle on the xy plane. And that gives you a symplectic structure, which is the same structure that you would have in the rest of classical mechanics. And then the possible distributions at that point are distributions on a sphere. So the space that you would have, where on a sphere for a polarization is much bigger because you can have all the possible distributions. I don't know if this makes any sense. I'm trying to condense a lot of things in a minute, but that's sort of the difference. Yeah. So one of the things that it's tricky is that quantum mechanics sort of has some aspects of discrete classical spaces and some aspects of the continuous of the phase space, and so it's easy to get confused because you can do some things in one way, some things in the other, and again, that's kind of why I think now I'm ready to write this reverse physics chapter for quantum mechanics, because I think I have explored the space enough that I will be able to clarify all these things while I'm writing them down. It might be that some of them are not even clear in my head right now, but they will be while I'm forced to write them out and say, okay, this condition is actually different from this thing, and then there is Tobias that tells me that I need the polarization identity to go from norm to inner product. Like there is all these little details, but okay. So where was I? Okay, so we did that conservation of norm is essentially conservation of probability, which means that it's evolution of the determinism and reversible. The evolution is deterministic and reversible. If I know the initial state with 100% probability, yes, I should actually say that. If the quantum mechanics probabilistic theory, this translates as being able to predict final errors. That is, and then state in terms of probability. That is, if I know the initial state with 100% probability, I will know the final state with 100% probability and vice versa. There you go. And so essentially the preservation of the inner product is that you're preserving all probabilities. And that's because the probability distribution get mapped. And so we have this, and then we're going to do it in terms of entropy. Then we want, okay, so now we want to do it the thermodynamic thing where we don't really have a thermodynamic entropy in quantum mechanics, so we can't appeal to quantum mechanics in terms of that, but we can appeal to quantum mechanics in terms of quasi-static evolution, making small transitions that are sort of that are reversible in these elements. Will we have talked about the inner product before this or not? What we decide? We decided to, yes, okay, projection we're going to talk about later, so I can't make that argument so well right now, but I can still say that this is sort of a quasi-static evolution. No, I can't say that it's a quasi-static evolution if I didn't say that. How can I word it? Okay, so now that in quantum mechanics both information entropy and thermodynamic entropy coincide in the sense that we do not have two different definitions in quantum statistical mechanics. So the condition is stronger in quantum mechanics. It is enough to record the full. In classical mechanics would only recover the preservation of. Okay, so this I saying here it's completely idiotic, and I shouldn't say. So this is where I don't understand even what I write. So in classical mechanics, deterministic and reversible evolution recovers the full Hamiltonian mechanics, but the point is that you need to have the independence of degree of freedom that is already bundled in the definition of state space, and it's going to be the same in quantum mechanics. The orthogonality of the degrees of freedom is already bundled inside the inner product, so that's absolutely equivalent. Okay, so this we remove. And what we want to say then is that the infinitesimal time step makes a change, but the change is reversible. Why don't I put this as the last? If I put this as the last condition, then it's a perfect segue for the next chapter where I will say, well, projector can be understood as processes with equilibrium. That's how it's going to work. Okay, so this is going to be, okay, this is going to be last condition. Because I noted that in quantum mechanics, both information entropy and, for example, in the sense that we do not have two different definitions in quantum statistical mechanics, okay. We can show, however, is that unitary evolution can be understood as an infinite sequence of projections that perturb the system minimally. As we saw, okay, so I should give the example here. Okay, let's see. Nick, does Shannon entropy of projection measurement, I think you referred to as entropy of coefficient somewhere, has any role in this? So the way that we want to say things is that when you do a projective measurement, but you do not look at the result, right? Then the entropy is going to increase. So for example, the idea is that if you have the the Bloch sphere, and you have a state that is prepared in spin right, and you want to measure either spin up or down. When you make the projection, this first gets mapped to a mixed state, and that's the idea of, oh, I made the measurement, I made the projective measurement, but I don't know the result yet, so I'm in a mixed state. And then when you look at the result, you update your state of knowledge. That part is really just updating state of knowledge. You go from that mixed state to either spin up or spin down. And so that part of updating becomes like the classical mechanics, because even in classical mechanics, I give you a probability because I'm producing things that you don't know. Then you do your experiment, you know something, and then you update your probability based on what you measured. So it's sort of a redefinition of the boundaries of the system. It's essentially what it is. But the part where you go from the pure state to the project mixed state, that really looks like essentially an entropic process, a going out of equilibria and getting another set of equilibria. And we are going to be able to show that that's exactly what we're going to have to see, that the conditions are exactly equivalent, and that's part of the next section. And so if by entropy of a projective measure you mean that the fact that you go to the mixed state and that increases the entropy, then yes, that's sort of our idea of saying that's a thermodynamic process. You did something. And the idea is that you are going to be able to see, this is what I want to write right now, the Schrödinger evolution as a sort of a series of infinitesimal projections where the axis on which you are projected that depends on the initial state, and it's infinitesimally close. So you can understand that if you have a rotation on the Bloch sphere, that would be a unitary evolution, and it's like you're always projecting to the axis that it's closest, and then effectively rotating. And I'm gonna make the example here in terms of the spin 1/2 system. So suppose that you prepare a spin 1/2 system in the horizontal direction, and then measure the vertical direction. The chance you have equal chance of measuring spin up or spin down. Now suppose you put a polarizer, I forget the names, so suppose you measure, put a polar, I have to check, this is a thought example that it's not that uncommon. Polarizer, I'll have to check what that is, at a 45-degree angle in between. The spin will the system, there will be two projections, first on the 45-degree angle, and then in the vertical, then along the vertical direction. The chance of ending in the vertical directions now is greater than ending in the chance of ending in the up state is now greater than ending in the down state. You can imagine inserting other two polarizers, and we'll have to see what else in between again, making 4 projections at a 22 degree angle between each pair. The chance of ending up in the up state is even greater. We can imagine then that if we put infinitely many steps at infinitesimal angles, the final state will be with the chance of being in the up state at the end will be 100%. We saw, in fact, that for a unitary evolution, psi of t plus dt psi of t is equal to 1. That is we say that for unitary representation, that is the projection of the of the state at a future time step on the previous time step is 1. This can be understood as making a projective measurement on an observable that is slightly different to one for which psi of t is an eigenstate. That is, we can understand unitary evolution as an infinitesimal sequence of projections at each time step. Another way of understanding this is that determinism and reversibility can be used for both measuring and preparing states. That is, if we prepare a system in a given state, we can use a unitary evolution to prepare a system in the future state. Conversely, if we can measure a state, if we measure a system in a given state, we can use unitary evolution to infer the state of the system in a prior at a prior time. And this is incorrect, reversibility. Therefore, we can understand determinism and reversibility as a series of preparations or measurements, and measurements in quantum mechanics are projections. Since measurements in quantum mechanics are projection, it makes sense that we can understand unitary evolution as a sequence of projections. Therefore, and then let's call this pronounce sequence, I don't know, projection P sequence, a projection sequence, there you go. Sequence. The evolution is an infinite, like a sequence of measurements at each time step is equivalent to ref det ref. Okay, and then this could then lead in to the projection and talk about that. That makes sense, but we need to put the other conditions first. Okay, so for me, pure mixed process is simply an entangling with environment, auxiliary beacon, and then discarding it, throwing away the correct. Yeah, so in quantum mechanics, you can certainly see any mixture as being something entangled with something that you throw away. Yes. Or you can just say nothing and say, you know, my entropy went up. But even in classical mechanics, right, when you say that the entropy goes up, most of the time you think in the back of your head that some system outside, you know, came in and disturbed the system and put in entropy. So it's not different. And again, one of the things that people think it's different in classical mechanics is the fact that in quantum mechanics, in classical mechanics, they think you can't see any mixed state as you can't purify mixed state. You can't say I have a pure state and then I see it as the marginal of something else. But that is true in classical mechanics only if you assume that points in phase space, like you can actually make delta diracs. Like the joint distribution is actually a point. If you say, well, those things don't really exist because they don't, then you can do something similar. You can take a distribution in classical mechanics and say, oh, this distribution actually comes from the marginal that has a correlation with some other system, and the entropy of the marginal is actually lower than the entropy of the joint is actually lower than the sum of the entropy of the marginals, which is exactly what you have in an entangled system for quantum mechanics. An entangled system is where the entropy of the joint is lower than the sum of the entropy of the marginals because you have some mutual information and therefore. So at the end of the day, if you look at things like this, it's not that different from classical mechanics or quantum mechanics. An entangled state is just a state where you have correlations between systems, and so you can always say my uncertainty of my state comes because there is some correlation with something else that came in and did something. So yeah, so these are the things that I need to sort of fully flesh out inside this whole thing. Okay, so so we have this condition, which is projection sequence. We have inferior, and I think what else is missing? Conservation of entropy we've done. Continuous series of measurements done. Conservation probability we have done, and yeah, we can put this, and we can put it essentially after we say that the evolution is deterministic evolution. So this so the same argument can be done can be developed on probability distributions. Suppose that we have a mixed state, meaning that it can be understood as a classical mixture of what? Of a set of orthonormal or orthogonal states. This is going to reuse the same argument. So suppose that we have a mixture, meaning that it can be understood as a mixture as well as state. If we have a deterministic and reversible evolution, we will be able to map the same distribution to another set of final state such that the probability remains unchanged. That is, if we are able to write yeah, I should have it here. There we go. We must be able to, we must have rho of delta t, there you got this thing, rho of t plus delta t equal to that stuff. Okay, if you're able to write rho of t, we must have the rho that is this will mean that okay, those remain unchanged. For that to work, the final set of states must be orthogonal to each other. Therefore, transporting therefore the ability therefore if the process transports probability distributions from initial to final observers, then it must map orthonormal basis to orthonormal basis. This means the evolution is unitary, and so prob trans, this evolution is unitary, and evolution maps preserves probability distributions is another physical, another equivalent conditions. So what I want to say about this, what do I want to say about this? The idea here is that in the end determinism and reversibility is effectively a permutation of objects while keeping like infinitesimally close states, i.e. differentiability, and they're keeping states keeping states as close, keeping the closeness, i.e. the differentiable topology, and the distance, i.e. the inner product, the same. Okay, maybe I can develop it better, but then I want to be able to say that. And so this is essentially all the conditions that I have for now in my head, right? Okay, so since it's already 12:40, I think it's gonna be more or less here. I will have to reread this whole thing. The prose still needs gonna work, but we start with the Schrödinger equation. Then we show that the Schrödinger version is unitary, and that's equivalent to that. And then we show that unitarity preserves the norm, and preserving the norm preserves the inner product. And it also preserves the norm, and preserving the norm is the same as preserving the inner product. Then it preserves a Born rule between initial and final states, infinitesimally close to each other, and it's not really preserve the Born rules. This might be the wrong name. It's like probability 1 to measure the next one, and the change is orthogonal to the initial one, and it changes maps orthonormal basis to orthonormal basis. And then we say we have determinism and reversibility because 100% gets predicted with 100%, or we can see this determinism and reversibility as mapping distribution from future and past variables, and then we can see this evolution as preserving the entropy, because if I map the variable to another and I preserve the distribution, then of course I'm going to preserve the entropy, and then I can see the thing as a sequence of projection. So I think this, do I have anything else? In classical mechanics we had determinism, reversibility, thermodynamic entropy, information entropy, and uncertainty in terms of, yeah, so if there would be, yeah, I don't think I'm going to be able to make anything with the covariance matrix in quantum mechanics. So I think that's basically it. I need to get out into the sun. Bye, Tobias. I think I'm done anyway, so I don't think I want to start anything new right now. If there are questions from the chat and you guys want to chat about something, I'll certainly be glad to do that. Otherwise, if there are no questions and nothing in the chat, I think we can call it a day. And thank you everybody for your company and participation. Okay, so I don't see any question from the chat. I hope I waited enough for a delay. I'll wait another 10 seconds. Okay, so we'll cut it here then.